welcome to this problem walkthrough. Today, we'll dive into the problem titled Minimum Number of Arrows to Burst Balloons. This is a fascinating problem that involves interval manipulation and optimization strategies. We'll explore different approaches to solving it and break down the key concepts you need to know. Let's get started. The problem asks us to determine the minimum number of arrows required to burst a collection of balloons. Each balloon is represented as a horizontal interval on the x-axis, defined by its start and end points. For example, if a balloon's diameter is represented by x_start, x_end, it spans from x_start to x_end horizontally. To burst a balloon, we can shoot a vertical arrow at any x-coordinate. If the arrow intersects the balloon's horizontal diameter, that balloon is burst. Our goal is to minimize the number of arrows required to burst all the balloons in the input. The input is a list of such intervals, where each interval represents a balloon's diameter, and the constraints ensure there can be up to 10,000 balloons with diameters ranging across a wide range of x values. The output should be a single integer, representing the fewest arrows needed to burst all the balloons. Now, let's look at an example to clarify. Suppose the input is points equals 10, 16, 2, 8, 1, 6, 7, 12. Here, we have 4 balloons with their respective diameters. To minimize the number of arrows, we could shoot one arrow at x equals 6. This arrow intersects 2 balloons, 2, 8, and 1, 6, bursting both. Then, we can shoot another arrow at x equals 11, which intersects the remaining 2 balloons, 10, 16, and 7, 12. This way, all balloons are burst with just 2 arrows. Therefore, the output for this example is 2, as we needed 2 arrows in total. In another example, the input is points equals 1, 2, 3, 4, 5, 6, 7, 8. Here, each balloon's diameter is completely isolated, meaning no 2 balloons overlap. As a result, each balloon must be burst with its own arrow. One arrow can be shot at x equals 2 for the first balloon, another at x equals 4 for the second, and so on. In total, 4 arrows are required, which is the output. Conversely, in a scenario like points equals 1, 2, 2, 3, 3, 4, 4, 5, some balloons do overlap. For this case, one arrow at x equals 2 can burst the first 2 balloons, and another arrow at x equals 4 can burst the last 2. Thus, only 2 arrows are needed for this input. To summarize, the solution must account for various constraints and handle edge cases efficiently. For instance, if there's only one balloon, only one arrow is needed. If all balloons overlap, such as points equals 1, 10, 2, 9, 3, 8, one arrow is sufficient to burst them all. Conversely, if no balloons overlap, one arrow is needed per balloon. Lastly, given the constraint that there can be up to 10,000 balloons, the solution must be performant and efficient, ensuring it works well even for the largest inputs. By carefully analyzing overlaps and shooting arrows strategically, we can achieve the minimum number of arrows in all scenarios. To approach this problem, we first consider the brute force method. The intuition here is simple. For each balloon, we examine all other balloons to figure out the minimum number of arrows required to burst it. This involves manually resolving overlaps between intervals through nested iterations. While this approach might seem straightforward conceptually, the challenge is its inefficiency. With each balloon requiring a full pass over all others, the time complexity becomes n squared. For small inputs, this might work, but when the number of balloons, n, reaches tens of thousands, this method quickly becomes impractical. So, while it's a good starting point for understanding the problem, it's clear we need a more efficient strategy. Next, we turn to the greedy approach. Here, the key observation is that minimizing the number of arrows is equivalent to minimizing the number of non-overlapping groups of intervals. By sorting the balloons based on their end points, we can prioritize bursting as many as possible with a single arrow. This forms the foundation of a more efficient solution. Building on this greedy strategy, we begin by sorting the intervals based on their end points. This ensures that we always consider balloons in the order that allows for the earliest possible burst. We then initialize 2 variables, arrows to keep track of the total number of arrows used, and last_shot to record the x-coordinate where the last arrow was fired. As we iterate through the sorted intervals, we check the starting point of each balloon. If the start of a balloon is after the last underscore shot, it means the balloon cannot be burst with the previous arrow. In this case, we fire a new arrow, increment the arrow's count, and update last underscore shot to the current balloon's end coordinate. However, if the balloon starts before or at last underscore shot, it means it overlaps with the previous group and can be burst with the same arrow. This approach only requires a single pass through the intervals after sorting, making it highly efficient. Sorting takes O(n) log n, while iterating through the intervals takes O(n), resulting in an overall time complexity of O(n) log n. While dynamic programming could theoretically be used, it introduces unnecessary overhead since the greedy method already solves the problem optimally. With the greedy approach clearly being the most efficient and straightforward solution, we can summarize the final algorithm. First, we sort the balloons by their endpoints to ensure we process them in the optimal order. Next, we initialize arrows to 0 and set last underscore shot to -infinity to represent that no arrows have been fired yet. Then, we iterate through the sorted list of intervals. For each balloon, we check if its starting point is greater than last underscore shot. If so, we fire a new arrow, increment the arrow's counter, and update last underscore shot to the balloon's endpoint. This ensures that we burst as many overlapping balloons as possible with each arrow. Once the loop completes, we return the total count of arrows. This algorithm is both elegant and efficient, leveraging sorting and a single pass to achieve the optimal result. By avoiding the complexity of dynamic programming or the inefficiency of brute force, the greedy solution stands out as the ideal approach for this problem. The problem asks us to determine the minimum number of arrows required to burst all balloons. Each balloon is represented as an interval, x_start, x_end, on a horizontal axis, and an arrow shot at position x bursts any balloon whose range includes x. The key to solving this problem efficiently lies in minimizing overlaps between balloons. To achieve that, we use a greedy strategy where we first sort the intervals by their ending positions, x_end. This approach prioritizes balloons that finish earlier, allowing us to minimize the number of arrows needed. For example, given the input 1, 6, 2, 8, 7, 12, 10, 16, we interpret it as 4 balloons with corresponding ranges. After sorting these intervals by their endpoints, the order remains the same: 1, 6, 2, 8, 7, 12, 10, 16. This sorted order makes it easier to determine the optimal points for shooting arrows and reducing overlaps. Once the intervals are sorted by their ending positions, we proceed with the main algorithm. First, we initialize 2 variables, arrow_count to track the number of arrows used, starting at 0, and arrow_position to keep track of the last position where an arrow was shot, initialized to a very small value like -infinity. Then, we iterate through the sorted intervals. For each balloon, we check if its starting position, x_start, is greater than the current arrow_position. If it is, this balloon cannot be burst by the last arrow, so we increment arrow_count and shoot a new arrow at the balloon's end position, updating arrow_position to this value. If the balloon's starting position is within the range of the last arrow, no new arrow is needed. At the end, the total arrow_count gives us the minimum number of arrows required to burst all the balloons. The efficiency of this algorithm stems from a few key insights. First, sorting the balloons by their ending positions ensures that we handle the intervals in the most optimal order, minimizing overlaps. Next, the greedy choice of shooting an arrow at the end of the current interval is optimal because it bursts the maximum number of overlapping balloons at once. For example, when intervals are nested, like 1, 10, and 2, 5, an arrow at position 10 bursts both balloons. Similarly, for disjoint balloons, each requires its own arrow. This strategy also handles edge cases, such as a single balloon requiring just one arrow, or fully nested intervals needing only one arrow for the outermost range. The algorithm relies on simple data structures, an array to store the intervals in 2 variables, arrow_count and arrow_position, making it efficient and straightforward. The algorithm is not just simple but also efficient. The time complexity is O(n*log n, where n is the number of balloons. This comes from sorting the intervals, which dominates the runtime. Iterating through the intervals to determine the arrow positions takes O(n), so the overall complexity is O(n*log n). The space complexity is O(1), as the sorting can be done in place, and no additional data structures are used beyond the input array and a few variables. To see this in action, consider the input 10, 16, 2, 8, 1, 6, 7, 12. First, we sort the intervals by their endpoints, resulting in 1, 6, 2, 8, 7, 12, 10, 16. Then, we initialize arrow_count to 0 and arrow_position to -infinity, preparing to iterate through the balloons. Now, we iterate through the sorted intervals to burst the balloons. For the first balloon 1, 6, since arrow_position is less than its starting point 1, we shoot an arrow at position 6. This increases arrow_count to 1 and updates arrow_position to 6. For the second balloon 2, 8, its starting point 2 is within the range of the last arrow, so no new arrow is needed. Moving to the third balloon 7, 12, its starting point 7 is outside the range of the last arrow, so we shoot a new arrow at position 12. This increments arrow_count to 2 and updates arrow_position to 12. Finally, for the fourth balloon 10, 16, its starting point 10 is within the range of the last arrow, so no new arrow is needed. The result is a minimum of 2 arrows. For edge cases, a single balloon like 5, 10 requires just 1 arrow. Disjoint balloons like 1, 2, 3, 4, 5, 6 each require their own arrow, resulting in 3 arrows. Nested intervals like 1, 10, 2, 5, 6, 7 need only 1 arrow for the outermost interval. This algorithm uses a greedy strategy to ensure efficiency and optimality. By focusing on the earliest ending intervals, we minimize overlap and reduce the number of arrows needed to burst all balloons. The approach is not only computationally efficient, with a time complexity of O(n)log n, but also handles various edge cases gracefully. Whether dealing with nested intervals, disjoint balloons, or a single balloon, the algorithm ensures the correct result with minimal computation. This highlights the power of combining sorting with a well-designed greedy strategy to solve interval-based problems effectively. The provided solution to the problem uses a greedy algorithm to minimize the number of arrows required to burst all balloons. Here's a detailed explanation. 1. Edge case handling. If the input list points is empty, no balloons exist, and the function immediately returns 0. 2. Sorting by ending points. The balloons are sorted based on their ending coordinates. This is a key step in the greedy approach, as it allows us to efficiently determine when an arrow can burst multiple balloons. The sort function is used with a lambda function to extract the second element of each interval. 3. Initialize variables. The algorithm initializes arrows to 1 since at least 1 arrow is always required. The variable arrow_position is set to the ending point of the first balloon after sorting. For iterate through balloons, the algorithm iterates through the sorted intervals starting from the second balloon. For each balloon, if the starting point of the current balloon is greater than the arrow_position, i.e., the current arrow cannot burst this balloon, a new arrow is needed. The arrows count as increment, and the arrow_position is updated to the ending point of the current balloon. If the current balloon's starting point is within the range of the current arrow, the arrow can burst it, so no changes are made. 5. Return the result. After iterating through all the balloons, the total number of arrows needed is returned. ###complexity analysis. Time complexity. The sorting step dominates the runtime, so the complexity is O(n)log n, where n is the number of balloons. Space complexity. The algorithm uses O(1) additional space, as the sorting is done in place. This greedy approach is efficient and ensures that the number of arrows is minimized while correctly handling all edge cases, such as overlapping and non-overlapping intervals. Here, we start by importing the necessary packages and defining our solution class. The key method here is findMinArrowShots, which takes a 2D array points representing the intervals of balloons. Each subarray has 2 values, the start and end positions of a balloon. First, we handle the edge case where there are no balloons. If the input is null or empty, we simply return 0 since no arrows are needed. Next, we sort the balloons by their ending points using arrays.sort. Sorting by the end positions ensures that we can use the greedy approach effectively, minimizing the number of arrows required. After sorting, we initialize the number of arrows to 1, as at least 1 arrow is needed to burst the first balloon. We also set the arrow position to the end of the first balloon, which represents the position where the first arrow is shot. Now, we iterate through the sorted intervals, starting from the second balloon. For each balloon, we check if its start point is greater than the current arrow position. If it is, this means the current arrow cannot burst this balloon, so we increment our arrow count and update arrow position to the end of the current balloon. This ensures that the new arrow is placed optimally to burst as many upcoming balloons as possible. Finally, once we've processed all the balloons, we return the total number of arrows required. This implementation is efficient, with a time complexity dominated by the sorting step, which is O, n log n, where n is the number of balloons. The traversal through the intervals is linear, making this approach well suited for large input sizes. Here, we begin with an example where the balloons have some overlap. The input is a list of intervals representing the balloons, and our task is to determine the minimum number of arrows needed to burst them all. First, we check if the input is empty. Since it's not, we move forward and sort the balloons by their ending points. This helps us efficiently determine the optimal placement for the arrows. After sorting, the intervals remain the same: 1, 6, 2, 8, 7, 12, 10, 16. Next, we initialize two variables. We start with one arrow, as at least one will always be needed, and we place this arrow at the end of the first balloon, which is position 6. Now, as we traverse through the sorted intervals, we evaluate whether the current balloon can be burst by the arrow at position 6. The second balloon, 2, 8, starts at 2, which is less than or equal to 6, so it can be burst by the same arrow. For the third balloon, 7, 12, its start point is 7, which is greater than 6. This means we need a new arrow. We increment the arrow count to 2 and update the arrow position to 12, the end of the third balloon. Finally, the fourth balloon, 10, 16, starts at 10, which is less than or equal to 12, so no new arrow is needed. The output is 2 arrows, as that's the minimum required to burst all the balloons in this case. Now, let's consider a case where the balloons fully overlap. The input intervals are 1, 10, 2, 9, 3, 8, 4, 7. Again, we start by checking if the input is empty, and since it's not, we proceed. Sorting these intervals by their ending points results in 4, 7, 3, 8, 2, 9, 1, 10. This ensures we can burst as many balloons as possible with the minimum number of arrows. We initialize our variables: one arrow, placed at the end of the first balloon, which is position 7. As we traverse the sorted intervals, we see that the start point of every subsequent balloon is less than or equal to 7. Specifically, for the second balloon, 3, 8, its start point is 3, for the third balloon, 2, 9, it's 2, and for the fourth balloon, 1, 10, it's 1. Since all these start points are less than or equal to the current arrow position of 7, no additional arrows are needed. The single arrow at position 7 bursts all the balloons. The output is therefore 1 arrow, which is the minimum required in this scenario. Here's an example where the balloons do not overlap at all. The input intervals are 1, 2, 3, 4, 5, 6, 7, 8. After confirming the input is not empty, we sort the intervals by their ending points, resulting in the same order: 1, 2, 3, 4, 5, 6, 7, 8. We initialize our variables with one arrow, placed at the end of the first balloon, which is position 2. As we traverse the intervals, we find that the start point of each subsequent balloon is greater than the current arrow position. For the second balloon, 3 of 4, its start point is 3, which is greater than 2. This means a new arrow is needed. We increment the arrow count to 2 and update the arrow position to 4. Similarly, for the third balloon, 5 of 6, its start point is 5, requiring another arrow. We increment the arrow count to 3 and update the position to 6. Finally, for the fourth balloon, 7, 8, its start point is 7, requiring yet another arrow. We increment the arrow count to 4 and update the position to 8. Since there's no overlap between any of the balloons, each one requires its own arrow. The output is 4 arrows, which is the minimum required in this case. To summarize, there are some key observations that help us solve this problem efficiently. First, sorting the balloons by their ending points ensures that we always consider the optimal position for each arrow. This minimizes the number of arrows required. Second, every arrow is placed strategically at the end of a balloon interval, which maximizes the number of overlapping balloons it can burst. Finally, the decision to use a new arrow is based on whether the start point of the current balloon is beyond the position of the last arrow. If the start point is within the range of the current arrow, no new arrow is needed. These principles ensure that we arrive at the correct solution using the minimum number of arrows. The time complexity of this solution can be understood by analyzing its major components. First, we have the sorting step, where the input list of intervals, represented as points, is sorted based on their ending points. This sorting operation uses Python's built-in sort function, which has a time complexity of O n log n, where n is the number of intervals. This step is the most computationally expensive part of the algorithm. After sorting, the algorithm iterates through the sorted list to determine the minimum number of arrows required. This traversal involves a single loop, which runs in O n time, as it processes each interval exactly once. When we combine these two steps, the sorting step dominates, resulting in an overall time complexity of O n log n. Now, let's consider the best, average, and worst cases for the algorithm. In the best case scenario, even if all the intervals overlap completely requiring the fewest arrows, the algorithm must still sort the input, making the time complexity O n log n. For the average case, where intervals partially overlap, the time complexity remains O n log n, because the sorting step still dominates. Similarly, in the worst case, where no intervals overlap and each balloon requires its own arrow, the time complexity is unchanged at O n log n. Shifting to space complexity, the algorithm passes the input points by reference, so no additional space is required for storing the input. However, the sorting step uses Python's timsort algorithm, which can require O n additional space in the worst case for temporary memory during merging. Beyond sorting, the algorithm uses only a constant amount of extra space for variables such as arrows to count the number of arrows and arrow_position to track the position of the last arrow. Since no additional data structures are used, the overall space complexity remains O n, dominated by the temporary memory allocation during sorting. To compare, a naive or brute force approach would involve checking all pairs of intervals to determine overlaps, which could result in a time complexity of O n squared. In contrast, the current approach optimizes this by leveraging sorting and a greedy strategy, reducing the time complexity to O n log n. This ensures that the intervals are processed in an efficient and structured manner, minimizing redundant computations. To further solidify the reasoning behind the big O analysis, sorting the intervals is an O n log n operation due to the timsort algorithm. The subsequent traversal step, which evaluates each interval and calculates the minimum number of arrows, runs in O n. However, since the O n log n sorting step dominates, the overall time complexity of the algorithm is O n log n. On the space complexity side, the temporary memory used during sorting results in a space complexity of O n. This balance of time and space efficiency makes the solution both practical and optimized for processing a large number of intervals. There are a few common mistakes to watch out for when solving interval-based problems like this one. First, failing to sort the input intervals is a big issue. Sorting, especially by start or end points, is often the foundation of efficient and correct solutions. Without it, you'll likely encounter logical errors or higher complexity. Next, assuming a greedy approach will work without justification can lead to suboptimal solutions. It's important to validate why your choice at each step is globally optimal and aligns with the problem's constraints. Another mistake is overcomplicating the solution. Many interval problems have elegant solutions with O n log n complexity that leverage sorting, so avoid unnecessary nested loops or extra data structures that increase overhead. Finally, neglecting edge cases can derail your logic. For example, intervals with zero width, overlapping intervals, or completely disjoint intervals should all be tested to ensure your solution is robust and error-free. Misunderstanding the problem statement is another major pitfall. For example, it's easy to misinterpret whether intervals are inclusive or exclusive, or confuse maximum versus minimum requirements. Misreading these details can lead to incorrect assumptions and flawed implementations. Now, when it comes to interviews, there are a few key insights to keep in mind. Recognizing patterns is critical. Many interval problems revolve around sorting and making decisions based on overlaps or disjoint intervals. Sorting is often the starting point, and understanding the role of start and end points is essential. Also, it's important to know when to use a greedy approach versus dynamic programming. For problems that ask for minimum or maximum counts, such as minimizing the number of arrows, greedy strategies are usually sufficient. Clear communication is another vital skill. Be sure to explain why your solution works, especially if you're using a greedy approach. Highlight the time complexity and why sorting is necessary. Lastly, always test edge cases during interviews. Scenarios like intervals with the same start or end points, or just a single interval, can demonstrate the robustness of your solution. When studying interval problems, exploring related problems can help deepen your understanding. For example, LeetCode 435, non-overlapping intervals, is another interval scheduling problem where the goal is to remove the minimum number of intervals to ensure the rest are non-overlapping. LeetCode 56, merge intervals, is a classic problem that focuses on merging overlapping intervals, which heavily relies on sorting and manipulating ranges. LeetCode 1288, remove covered intervals, involves identifying intervals that are completely covered by another and removing them, which requires careful analysis of start and end points. Finally, LeetCode 763, partition labels, is a variation that deals with dividing strings into non-overlapping partitions. While it's not a direct interval problem, it emphasizes concepts like grouping and non-overlap, making it a valuable addition to your study list. There are also alternative approaches to solving interval problems, each with its own trade-offs. A brute force approach, for example, involves checking all possible pairs of intervals for overlaps. While simple to implement, this results in n² complexity, which becomes infeasible for larger inputs. A more efficient and commonly used method is the greedy approach with sorting. By sorting the intervals based on endpoints or start points and making a single pass to determine overlaps or counts, you can achieve an optimal n log n time complexity. For more complex problems where decisions depend on multiple overlapping intervals, dynamic programming can be useful. However, this approach typically has n² time and n space complexity, which makes it less efficient than greedy methods for simpler scenarios. Lastly, the sweepline algorithm can handle more intricate interval problems. By processing event points and counting overlaps dynamically, this method is efficient for certain applications but requires careful implementation to manage edge cases and avoid errors. Great work! To recap, we tackled the problem of minimizing arrows to burst balloons. We learned how sorting and overlap analysis can lead to efficient solutions. Remember, interval problems are common in technical interviews, so practicing these is highly beneficial. Thank you for joining, and be sure to check out more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!